Okay, when we left off, we were looking at the limit laws. We developed this set of rules that I've got listed on the right here. And using those laws, we were then able to develop some additional rules about evaluating polynomials and rational functions. And to sum it up, it's simply that the limits of rational functions and polynomials are just their values everywhere they're defined. The problem is that many rational functions aren't defined everywhere. They have points where they can't be evaluated because of zeros in the denominator. And what if we're interested in the limits there? And in fact, we're going to be interested in the limits there. You might recall that the big reason we were looking at limits was to solve this problem of instantaneous rate of change or the tangent line at a point. And remember, the big issue was zeros in the denominator, right? So this is going to be crucial for helping us solve that problem. We're going to look at some other limits because, like I've said a couple times, this is not the only place limits are useful is in computing derivatives. This is this thing we haven't done yet. That's where we're going. But it's a really important one. So this is going to be a pretty big idea for us. So let's look at this function here. F of x is x squared minus 9 over x minus 3, a simple rational function. If we want to, we can see it's defined everywhere except at x minus 3. So if I wanted to, for instance, take the limit as x goes to 5 of f of x, according to this rule, I simply evaluate this function at 5. I get 16 over 2 or 8, right? That's no problem. That's where the rule works great. The problem comes in here, because g of 3, if the denominator evaluated at 3 is equal to 0, and so I can't simply evaluate it. I need to do something else. Here's the something else we're going to do. If I look at this expression, I might notice that I can factor the numerator. And then I notice there's a common factor that I can cancel, right? But I can't quite cancel it, right? I mean, I did, it's disappeared, but I need to note these two things are exactly the same. If I put any number into either one of them, the same thing happens, right? If I put 5 into both of them, 8 will come out. It doesn't matter which way I've written it. And you'll notice that if I put 5 into this one, 8 also comes out. This one, though, is different than these two because this one can be evaluated at 0. So these two things are only equal when x is not equal to 0. Sorry, not 0, 3. Right? The problem, we've seen this before, comes in because if x is equal to 3, I've got 0 over 0. That can't be canceled, right? Cancellation just means if you've got two of the same factor over each other, a thing divided by itself is equal to 1. So you just have you're multiplying by 1. It does nothing, so we just don't write it. It's not true when it's 0 over 0, right? So we can't do that move when x is equal to 3, okay? But everywhere else, these two things are the same. So let's consider these two functions. I've got f of x is equal to x squared minus 9 or x minus 3. And I've got g of x is equal to x plus 3. These two things are the same function everywhere. In other words, f of x is equal to g of x, except when x equals 3, right? So if I put in a number, let's put in something like, and actually I'm gonna write f of x as x plus 3, x minus 3 over x minus 3. That's exactly the same. Nothing's changed there, and I've got this. Let's just notice, if I put in a number like f of 3.1, I get 3.1 plus 3, 3.1 minus 3, over 3.1 minus 3. which is just 6.1, I'm adding those together. 6.1 times 0.1 over 0.1. This cancels, right? And we end up with 6.1, just like G of 3.1 is equal to 3 plus 3.1 or 6.1, right? So any number you put in, we can always cancel this factor, except when that factor is 0. So these two functions are exactly the same everywhere. The crucial point, not the crucial point, a crucial point about limits, remember, is it doesn't care about the point that it's taking the limit to, in the sense that it doesn't matter what the function does at that point. It only matters what it does near that point. When I'm taking the limit as x goes to 3, all I care about is what happens to the function as my values of x get closer and closer to 3, not at 3, right? So this is crucial. So now I have a function g that's exactly the same as f. In other words, it does all the same things that f does near 3, like f of 3.1 and g of 3.1 are the same. That's near 3. They do the same thing. If I took 3.00001, they both do the same thing, right? So everywhere near 3, these two functions do the same thing. Limits ask, what does my function do near 3? Then whatever g does near 3, f should do near 3. In other words, the limit as x goes to 3 of f of x, which we didn't know how to do because we had a 0 in the denominator, none of our rules told us what to do, should be the same as the limit as x goes to 3 of g of x, because they do the same thing near 3. The limit as x goes to 3 of g of x is just the limit of x plus 3. This is now a polynomial. We know what to do with polynomials. We simply evaluate them. And so this limit is 6, which tells me that the limit as x goes to 3 of f of x is equal to 6, even though the function isn't defined there. If we were to graph that function, let's do this. If we were to graph f of x, that function looks exactly like the line x plus 3. So there's my intercept. Try to get this about right. There's my graph, except that this, so at 3, somewhere about right here, whoops, it has a hole in it. Otherwise, it looks exactly like the line x plus 3 for all the reasons we just set up here. If we put in any values, we get the same things out. So we know what the line x plus 3 looks like. F of x must look exactly like that, except for this one place where it has an issue, where it has a 0 in the denominator. It has a hole in it. And so the limit doesn't care about that hole. It just notices this hole is happening at the point 3, 6. The limit just notices that as we take x values closer and closer to 3 from above and below, our y values are getting closer and closer to 6, all right? So this is a big rule for us. This is going to be a lot of what we do when we're trying to come up with these slopes of tangent lines, instantaneous rates of change, this thing we're going to eventually call the derivative. We're going to use this rule. So I've done it for these two particular functions. Let's just say it in general. If f of x is equal to g of x near a, except possibly at a, then the limit as x goes to a of f of x is equal to the limit as x goes to a of g of x. I'll put a parenthetical in here, provided the limit as x goes to a of g of x exists. So, right, in this case it did, right? If the thing we came up with still doesn't have a limit, then it doesn't help us, right? But when we use this strategy, generally we'll be finding things that do have limits. This is a big deal because this helps us get past this big idea of zeros in the denominators. So let's do a couple examples with this. Oh, let me just remind us again, near A means an open interval containing A. And that open interval, near, makes us think close. It's really any open interval. And in the case of the example we just did, those two functions are equal to each other on the open interval, negative infinity to infinity, except at x equals 3. So that open interval could be quite large. All right, let's do a couple more examples. Let's take a look at, these are going to be very similar to things we're going to see in the future. The limit as t goes to 0. Let's look at the square root of t squared plus 9 minus 3 over t squared. Right? So if you try evaluating the function, if you look at this function and put in the values 0 for t, you'll get 0 over 0, which is not defined, which we could do if you look through all of our limit laws. We could try to apply the limit law where we split it into the numerator and the denominator. In the numerator, we take the limit of the first term minus the limit of the second term. We use the limits for roots, right? If we could, that square root is a 1 over 2 exponent. We bring the limit inside, and then we use the polynomial thing. So we could go through all those steps, but we're going to end up with a 0 over 0, right? Which is problematic. So what we're going to do is look for a function that's equivalent to this one, except possibly at 0. So it's not obvious what to do, okay? So I'm going to show you a trick that somebody discovered at some point that turns out to work well. When you see something like this, a square root or a cube root, maybe a cube root, probably a fourth root, you might want to use this. Square roots will be very typical though. And this is a good example where when you're stuck on a problem, sometimes you just try something to see what happens, even if you're not sure where it goes. I'm not sure who discovered this trick, but I imagine that part of their discovery was just, let's just try some things and see if anything nice works out. So what we're going to do is multiply by what we call the radical conjugate. You might have heard of the complex conjugate. This is something similar. So we've got this addition or subtraction of terms in the numerator. One of them, at least one of them, has a radical in it. Well, I'm going to write the same thing, except instead of subtraction, I'm going to turn it into addition. If it were addition, we turn it into subtraction. That's the conjugate part. You reverse the sign. Now, if I multiply this by something, then it changes its value. And I don't want to change it. I want the same function. So how can I get the same function? I can get it by multiplying by 1. So I'm going to multiply by the exact same thing here. Just move over a bit. All right, so let's see what happens when we do this. Well, a nice thing happens in the numerator. T squared plus 9, the square root of t squared plus 9 times the square root of t squared plus 9 gives me t squared plus 9. I get a positive 3 times that radical and a negative 3 times that radical. Those cancel out. And then I get minus 3 times plus 3 gives me a minus 9. In the denominator, I'm not going to expand it. I'm just going to write it this way. So now notice what happens in the numerator. Those 9s cancel and I'm left with t squared over t squared times this radical conjugate. Now I've got t squared over t squared. I'm going to cancel those. Why am I allowed to do this? Well, the thing I'm writing now is not the same thing as the line above. These two things are not the same, right? However, they are the same when t is not equal to 0. And the one place I don't care about when I'm taking the limit as t approaches 0 is at 0. I care about all the other numbers, especially the ones close to 0, but I definitely do not care what happens at 0. So this thing here is the same as what we started with, right? In other words, these two things are the same whenever t is not equal to 0. So this is the function we were looking for. I now have an f and a g, right? F was the original one. G is this new one that are the same everywhere except for at 0, right? I got away with this because first of all I did was multiply by 1. If you multiply by something over itself, you're multiplying by 1. And I did a rule that we have to be careful with, the canceling, but that rule was fine because the only place it's problematic is at the place I don't care about. So what that means is, applying this rule, this limit, oops, let's get a pen, is equal to the limit as t goes to 0 of this new expression. Okay, and now I can apply all my limit laws. Remember, if I have the limit of a quotient, I can take the limit of the numerator and the denominator separately. I'm going to rewrite the square root as this power because remember we had this root rule written this way just to make it more familiar. I'm also going to apply the sum rule in the denominator. Well, I know the limit of the constant 1 is just 1. I'm going to apply my my rule for roots. I can take the limit inside and then take the square root. And then I know the limit of the constant 3 is just 3. Now I've got a limit inside that 1/2 power. I've got a limit of a polynomial, which I know is just to evaluate it. So this is just 0 squared plus 9 or 9. So I've got 9 to the 1/2 plus 3 or 1/6. And so the limit of this function, even though it's not defined at 0, what I know is that it gets closer and closer to 1/6. Okay, so that's the big idea here, that this thing, even though it's not defined there, we now know it gets closer and closer to 1/6. Why? Because we know it's the same as this function that is defined at 0, and they do the same things, and the limit there using the limit laws was 1/6, so the other one must be doing the same thing. It just has a hole in it at that spot, right? I don't need to know exactly what this looks like. I just know that that's what's happening, okay? All right, so this is a pretty common thing we're gonna see, this method of using, where did we go? This radical conjugate, right? When we've got some kind of radical plus or minus something, you change the sign of that plus or minus and multiply by that over itself. I could probably come up with a situation where it doesn't work, but it's definitely a good thing to try. The worst that could happen if we tried it and it doesn't work is we realize we need to try something else. All right, let's do one last example to end this video. Let's look at this limit. The limit as h goes to 0 of 1/2 plus h minus 1/2 over h. So here's another one. If we throw a 0 in there, we have a 0 in the denominator. It's problematic. So again, I want to use some algebra to try to find an equivalent function to take the limit of. So let's take a look at this. First, I want to look at the numerator on its own. The numerator here, and again, this strategy can go into a category of, if it's not working and you want to find something that does, sometimes you just play around. So the first thing I'm going to try is see if I can combine these into a single fraction and then see if that gets me anywhere, right? I hate compound fractions like this when we got fractions within fractions. I just hate them. They get just, in terms of notation, they just seem awful. They get really complicated. So even if I wasn't doing this, I would want to rewrite this because it seems like a horrible way to write it. So if I want a common denominator, I can just multiply each by the denominator. So the one on the left, I'm multiplying by 2 over 2. So it'll have 2 in the numerator, 2 over 2 times 2 plus h, and then I'll get 2 plus h over 2 times 2 plus h. So I can rewrite all of this as 2 minus 2 plus h over 2 times 2 plus h. I notice now that in the numerator, I got a minus 2 and a minus h. So 2 minus h leaves me with just minus h over 2 times 2 plus h. So this is a pretty nice configuration for the numerator. So let's put the fraction together now with this new thing in the numerator, negative h over 2 times 2 plus h. I've still got this double fraction though, which I hate. So instead of dividing by this h, dividing by a number is the same as multiplying by the reciprocal. So that's right. Dividing by 2 is the same as multiplying by 1/2. Dividing by h is the same as multiplying by 1 over h. And now I see what's going to work. I've got an h in the numerator and an h in the denominator factors. I'm going to cancel them. Once again, the thing that I'm ending up with, negative 1 over 2 times 2 plus h, I'm writing equals, but these are not the same, right? This one is not defined at h equals 0. This one is. This one is defined when h equals 0. We get negative 1/4, right? So they're not the same at that point, but they are the same everywhere else. Same reason. When we divided by this, when we're dividing by something, we have to be sure it's not equal to 0. We're allowed to do this as long as h is not 0. So if h is not 0, this is the same thing. When h is 0, these are different, but we don't care about 0. The limit only cares about all the other points, especially the ones near 0. So this limit is equal to the limit of this new expression, right? That's what my rule said. If I find a function the same as the one I want the limit of, except at that one point, then I can just take the limit of this new function. This new function is just a rational function, which we've already determined their limits are just the evaluation of the function at that point, as long as it's in the domain. And it is, we just evaluated it to be negative 1/4, plugging in 0. And so now we can take this limit of this expression with a 0 in the denominator. Okay, so I've shown you 3 examples now. We had a rational function where we factored it to cancel out the problematic factor and take the limit. That was our first big example. We saw this one where we use the concept of the radical conjugate to end up getting rid of a 0 in the denominator. And here we had one with some compound fractions that we manipulated until the 0 was gotten rid of, right? These are some pretty standard ones we're gonna see. This is certainly not comprehensive. We'll do some more examples in later videos, and there's plenty more out there. But a good rule of thumb is when you're finding you've got something like 0 over 0, that you can probably do some algebraic manipulation to get rid of that 0. Sometimes you can't, but it's always worth a try. Okay, that is it. Thanks everybody. I will see you next time.